We will have 2 contributor talks now and then a final plenary talk. And for the first contributor talk, I'm very happy to introduce David Wipf. David completed his PhD at UCSD San Diego, and then he spent a few years at Microsoft Research in Beijing. He's done very, very nice contributions at the intersection between sparse coding, Bayesian modeling, and machine learning. And he's now at Amazon AI labs in Shanghai, working on generative models and neural networks. So David, thank you so much for joining us here. We are very excited for your talk.
Okay, thanks a lot for the introduction and the opportunity to be here. I'll start just with a brief introduction to variational autoencoders. I suspect many people are familiar with them, but just a little bit of background. This is a very popular deep architecture. It's basically just a probabilistic extension of autoencoders, and it's one of the most commonly used generative models. So a regular autoencoder just takes some input X, it passes it through an encoder DNN, and then you get a compressed representation Z. Usually the dimension of Z is much less than the dimension of the original signal X. And then you pass that through a decoder deep neural network and you try and reconstruct it as accurately as possible. So the VAE, at least for continuous data, this entire talk will be about continuous VAE models. It's very similar to the regular autoencoder, except that now, instead of having a deterministic representation in the latent space, it's probabilistic. So the encoder DNN produces a mean function and a covariance function, typically, and these produce a Gaussian sample Z from some Gaussian posterior. So this is like a stochastic representation that then samples from this stochastic representation can pass through a decoder DNN and produce a new mean, mu X and sigma X. And then you can draw samples from this to also try and represent the probability distribution of the original X. And oftentimes for actually drawing samples, the sigma X, you ignore that part, but that's kind of a minor detail. So the basic idea behind this is predicated on a latent variable observation model. And you have some training data here. It's a big matrix X. Each column, X sub I, is one sample. And you assume it's from some parameterized distribution here. But we also assume this is coming from a latent variable model. So the idea is that you have some prior on these Z variables, typically a Gaussian, and you draw samples from those, and you pass it through this conditional distribution to get the output, or the parameterized distribution on X. But the problem is that this integral is usually intractable. So VAEs are based on a variational bound on this intractable distribution. So here the expression on the left is just the negative log likelihood summed over the training samples. And the idea is you would like to develop a tractable upper bound that you can actually train. So here you have two sets of parameters. The theta are the original parameters you really want to optimize. And the phi are parameters that control the bound. And you basically want the bound to be tight in regions of interest. And the VAE bound is constructed like this. It basically has two terms. There's a KL term, which is a regularization factor, which penalizes what is called a Q distribution. This could be any distribution you want. The bound holds regardless of the form of Q, but this is where the parameters of the VAE come from. And it penalizes the KL distance of this Q distribution from the prior. And then over here, you have a data fitting term. And this is the term that has the structure of an autoencoder. So you look at these two together. The first one is regularization. For the Gaussian choices for Q and P, you can get this in closed form. And then the data fitting term has an autoencoding structure because this Q distribution, you're drawing samples Z, that's like the stochastic encoder. And then the log P of X given Z, this is like a decoder. So the variational optimization problem, the VAE optimization, you can basically solve using stochastic gradient descent. And the typical choices for the Q and P are Gaussian, as I mentioned before. And you have deep neural networks that are encoding the mean and covariance for both the encoder and decoder distributions. So with all the different kinds of deep generative models, you might ask, why would you choose a variational autoencoder? And there are some underappreciated reasons why you might want to do that. Among other things, the VAE global minima can be used to isolate and remove sparse corruptions in training samples. So you don't actually need clean samples. And there's a way you can train it with the right parameterization. So you can take this kind of input image and you can clean it up. Another thing you can do is estimate the lowest dimensional manifold containing the clean training data. So here's a low dimensional manifold. The black dots are some samples along it. And you can use VAEs to get a low dimensional model, this purple dashed line that closely approximates the ground truth manifold. And this is where the optimal sparse representation comes in, because you want to have this low dimensional model be as tight as possible. You don't want to use too many extra degrees of freedom. And then finally, once you have this low dimensional manifold, you can consider generating realistic new samples within the manifold. So that could be faces or text or something else. So that's all about what you can at least do in principle with global minima in a VAE. But what about bad local minima? And there's comprehensive analysis only in some very simple special cases, really. So if you consider a linear decoder, so the mu of x function just equals a matrix, parameter matrix times the latent variable z, and just a simple single parameter decoder covariance. Lambda here is just a scalar. And so this is the parameterization of the decoder. And the encoder is similarly simple. You again have a linear model for the mean and just a fixed parameter diagonal covariance for that. And quite simple model, and a result that has recently been shown in a couple of papers is that any VAE local global minima in this limited regime, the columns, this WX star, the columns of this one will align with the top K principal components of the data. So this is a nice result because even in this simple case, there's a combinatorial number of local minima, but they're all global and they give you the top K principal components. But the limitation is we already know how to compute PCA. So the VAE is not really providing anything new here. So an alternative is to examine a case where no other known approach has a similar type of guarantee. And this is where we start looking at non-trivial optimal sparse representations. So what do I mean by this? It's basically, I'm thinking of something similar to finding the lowest dimensional manifold structure of the data. So more specifically, we have two VAE criteria for this kind of optimal sparse representation for present purposes. The first is optimal reconstructions. So that basically means you're taking samples from the posterior Q and passing them through the decoder mean, and you want to learn parameters such you can push this reconstruction error as close as possible to 0. And then the second is you want the maximal number of latent dimensions to be set to the prior. So here, z sub j is one of these, the jth dimension. And if the posterior here is equal to the prior for all of the training data I, then there's no benefit to the reconstruction. So it's like this dimension was shut off. It's not being used. And of course, you can have a deterministic criteria for AE models as well, just optimal reconstructions, maximal number of latent dimensions here set to just a fixed 0. And there's many advantages to these optimal sparse representations, such as generating sharp samples, feature learning, interpretability, such and such. So what about a more practical example? So here's where I get into multiple response sparse regression. So we have some observed data. This is just a big matrix, and X sub I are the columns. And the assumed ground truth model here is that X is decomposed into a dictionary phi of known features and unknown row sparse coefficients. Here, U naught. And this U naught is basically the optimal sparse representation because you want the most number of rows of it to be equal to 0. And this is a well-known NP-hard inverse problem. So if you want the U naught under some special, relatively minor circumstances, you basically minimize this row naught. This row naught is a count of the number of non-zero rows. So here this Uj is a row of U, and you're minimizing the number of them that don't equal 0 subject to the constraint. And there's a typical convex relaxation for this. It's a form of the group lasso. You just replace this counting measure with a mixed norm. You just sum the L2 norms over rows. And there's a lot of applications in things like neuroimaging, a lot of underdetermined inverse problems. Okay, so how do we align this multiple response regression problem with a VAE? So the VAE components for this will be deceptively simple, but still end up with a very interesting objective. So for the mean, we take the dictionary of features and we weight them by a diagonal parameter vector, diagonal matrix of parameters. And we keep the same simple decoder variance, just a single parameter. And then for the encoder, it's just basic affine linear function. So nothing too special here. And we have a very simple parameter set in total. So here's the resulting energy function you get when you go through and compute all the terms. And this is still non-convex, potentially many local minima. So it's unclear what you can get from this. And you can also consider an analogous autoencoder for multiple sparse regression. Here, this is like the decoder. The constraint is like the encoder. You can have a just typical weight decay like penalty for avoiding scaling ambiguity on these WX, and then some penalty promoting row sparsity here. And you can show that if you globally minimize this autoencoder with the right choices for this H function, you can basically minimize any constrained optimization problem with the row sparsity penalty. G prime. So whatever G prime you have, you can choose a corresponding H and you can solve something very similar to the original problem. Okay, so here's the main result, comparing this VAE model with a competing class of autoencoders. So assume, again, our data is generated like this from this decomposition into phi and row sparse U naught. And we're assuming the number of non-zero rows of this U are less than D. That's the number of, also the number of rows in X. And there's some other minor technical conditions I'm not going to mention. These are just to basically ensure the U naught is unique. It's not like in typical compressive sensing where you require coherence or RIP properties, stuff like that. It's much more loose than this. And just as some notation, when I add a star here, this is referring to any local minima of the VAE objective in the limit as this lambda goes to 0. This is just so you can get high quality reconstruction. The reconstruction errors can go to 0. And then finally, this pi sub j is the value of the jth largest row norm of U naught. So here's the main result. There will be a set of d minus 2 constants. These are these v sub j's in this interval between 0 and 1. And they're such that basically whenever there will always be a set of these type of constants such that for any u prime that satisfies this inequality, meaning that there's some kind of scaling ordering of the rows. They don't all have similar magnitude. As they become smaller and smaller, they have to be less than something less than 1 times the next biggest one above it. So it's a way of scaling the different row norms, the non-zero ones. So if this holds, we have that this U naught is a unique optimal sparse representation. These These local minima are also a VAE global minima. And the most interesting part is that this term here is actually the posterior mean computed with the optimal coefficients. And if you just rescale them, you actually can compute the U0, the ground truth U0. And there's no analogous autoencoder that can satisfy an equivalent recovery result. This is basically saying that all the bad local minima will be gone and the global minima will be uniquely aligned with the solution you're looking for. And but with the AE, there's no way you can rule out the bad local and or global minima. There's no way to always do that. And just in terms of applicability, the theory is related to sufficient but not necessary conditions for getting these optimal sparse representations. But it's solving a non-trivial sparse inverse problem. And there's no known alternative algorithm with a similar guarantee that I'm aware of. So this is quite unlike the PCA solution I mentioned earlier, where it's nice that the local minima are global, but we know how to do PCA. And just to illustrate when it kind of is more likely to hold this theorem, if you look at here a plot of like candidate non-zero row norms of this U0, here they all have very similar magnitudes of the row norms, the size. This is harder. The theory is less likely to apply here, and it's more likely to apply in a case where they have highly different scales. So as an extension, if you enforce that the encoder covariance is diagonal, the theory doesn't hold anymore, but you can get a weaker version of some local minima smoothing, but I don't have time to talk about that. So here's just a quick empirical example to show how this plays out numerically. Again, the goal to recover this U0 from these observations. And so I did a bunch of simulations here. In this case, the dictionary is just IED Gaussian, and the U0 has unit norm non-zero rows. So this is the hard case. And the y-axis is the success rate recovering the ground truth U0, and the x-axis is the number of ground truth informative dimensions. So the more informative dimensions you need to find, the harder it becomes. And so I compare a VAE, the autoencoder, and a group lasso. This is the convex standard tool for this problem. And interesting, the VAE and the AE for this case have the same global minima. So if and they're both aligned with the correct solution. So if they fail, it's because of convergence to a bad local solution. And you can see here that the VAE, even in this kind of worst case scenario, is doing better than the autoencoder and the group lasso. And on the right, we have the same situation, only now the U0 has these scaled non-zero rows and the performance moves dramatically to the right, meaning it's doing much better. And the other ones don't enjoy the same benefit. And here's a more practical example from neuromagnetic inverse modeling, where the phi is a mapping from a electromagnetic field in the brain to sensors on the scalp. So this lead field matrix, so-called in the literature, has very highly correlated columns. So convex algorithms, a lot of standard methods don't work. And you can see the VAE is still getting excellent performance, and the other ones, the performance kind of deteriorates pretty dramatically. Okay, I'll maybe skip this. This is to point out that these optimal sparse representations are very helpful for generating new samples. I'll include something about that in the paper and just summarize. Prior work has showed that VAE global optimum can oftentimes provably isolate and remove sparse outliers, estimate optimal low dimensional inlier manifolds, and generate ground truth samples within these inlier manifolds. But this is global optimal properties. There's been very little analysis about when you can avoid bad local minima. So there's really no strict guarantees about bad local minima in problems of interest. And so here we show a reasonably challenging regime where all VAE local minima can produce an optimal sparse representation. And this helps to explain the effectiveness of VAEs in modeling low dimensional structure beyond just their original use case of generative modeling. So thank you very much.
Thank you very much, David, for that nice talk. Maybe if there are some questions, I would encourage people to write them on the Q&A, or even to utilize the raise your hand that you have available in the options. And perhaps for the sake of time, just because we are running a couple of minutes late, we will move on to the next talk. But I would encourage everybody to keep your questions, and we can keep discussing them offline on Gather.